Now what about if we have a ratio? Now to calculate the finite expansion of a ratio, we have two methods. We will learn both, but we'll be using most of the time the second one. In the first method, we say that if we have a ratio and we have a finite expansion of f and a finite expansion of g, and we want to calculate the finite expansion of the ratio f over g to the order n in the neighborhood of n0, it's as if we are calculating the finite expansion of the product f times 1 over g. So we need to follow the calculation of the finite expansion of the product rules. In fact, if g can be written as g of x0 plus the polynomial of degree n plus the remainder, so I separated g of x0 plus the remaining part of the polynomial, and then 1 over g will be equal to 1 over this expression. And so I will take g of x0 as a common factor, which will give this expression in here. And then I will separate the g of x0, I will put it on the side, and then I will calculate the finite expansion of this term. Why? Because I already know the finite expansion of 1 over 1 plus x. So I will replace x by all this term, if I'm sure, of course, that this term goes to 0 when x tends to x0, and this is the case because g of x0 is not equal to 0, and this term goes to 0 as x tends to x0. So this is the strategy I will follow when calculating the finite expansion of 1 over g. So this is what I'm writing in here. This term, or this part, I will call it u, and I will use the finite expansion of 1 over 1 plus u, which is 1 minus u plus u squared, etc. And then I replace and I do the thing. I will show you this in an example. If I want to calculate the finite expansion of tangent x, which is the ratio of sine x over cosine x to the fourth order, then I am calculating here sine x to the fourth order, and then 1 over cosine x to the fourth order. But in here, I don't have to take anything in as a common factor because I'm starting by 1. But if I was starting by 2, I should have taken 2 as a common factor in order to have 1, as I did in the proof. So here I have 1, so I will use the expansion of 1 over 1 minus u, and u will be this part in here. And then doing so, and then expanding and removing the terms of order greater strictly than 4, I will obtain this as the finite expansion of 1 over cosine x. And now I multiply by x, and as you can see here, as I said in the remark earlier, so the term 5x4 over 24 will not contribute to this final result because it will be multiplied by at least by x, so it will give terms by x5 and more, so it will not contribute. Now let's look at this remark. If the finite expansion of g, which is in the denominator, to the order n starts with a non-zero constant, the division is always possible. As you saw, I should have g that starts with something not equal to 0, otherwise it doesn't work. I will not have the form 1 plus something in the denominator. Then even if the limit of g of x when x tends to x0 is 0, then the denominator will be starting by x at least, or x2 or x3. Then in this case, the division is possible only if the numerator will be starting also by x. So if down there it's starting by x2, the numerator should be starting by x2. Otherwise the division is not possible. Because if this is the case, we can take x2 as a common factor up there and x2 in the denominator as well, and then simplify these x2's, and I will have 1 plus something in the denominator again. Okay, so again, if g starts with a constant not equal to 0, it's good. If it starts with if g of x0 is equal to 0, or the limit of g of x when x tends to x0 is equal to 0, so it's starting with a term including x, a power of x, then the division is possible only if the numerator is starting with the same order. Then I can take a common factor and then simplify it. But in this case, you should watch out for something. If I'm asking for a finite expansion to the order 4, let's say, and if you do so, you will lose x2 from the numerator, so your terms will be like 1 plus x2 at the end. You will not have the terms x3 and x4. So if this is the case, you should go to the order 6 in the numerator, so that when you take x2 in common factor and you simplify it, you will still have all the terms that can contribute to the order 4. I will show you what does it mean. If I want to calculate, for example, the finite expansion of this ratio, I will look to the denominator. I am starts with degree 1. So automatically what you will do is that if I'm asking for an order 2, you will calculate the numerator to the order 2 plus 1, which is equal to 3, and then do the same in here, and then denominator to the order 3 as well. Okay, so that's what I'm writing in here. If in this case, so this case is if the finite expansion starts by a power k, so in this case we compute the finite expansion of f, the numerator, to the order n plus k. If I'm asking for an order n, you will calculate for n plus k, you will add the minimal degree of g, the degree by which the g is starting, and then you will calculate also g to the order n plus k, so f plus g. So this is what I did in here. I calculated both to the order 3, and then I should take like x in common in the numerator and in the denominator and simplify it and do what I did before. So I have to calculate the expansion of 1 over 1 plus what remains and multiply it by the numerator. So this is a very important remark. Pay attention to it. And finally, I will end up with a second degree expansion, although I was starting with third degree expansions, but I lost one order during the calculations. Now for the second method, it's more practical, it can go faster in fact. So we have the same hypothesis. We should have f over g, and f should start with a term of degree greater or equal to the degree of the first term of the finite expansion of g, as I said before. Then if I'm asking for an expansion to the order n, you should calculate expansions in the numerator and the denominator to the order n plus k if k is the the order of the term which is the starting term or the first term in the expansion of g. So for example, if I want to recalculate the expansion of tangent x here, the method is the method of division, Euclidean division, but according to the increasing exponents of x. What does it mean? If I want to calculate the expansion of tangent x, I will use this method. I will put in here the of course the expansion of the numerator, and in here the expansion of the denominator. So here it's sine x and here is cosine x, and then be careful that I put both expansions in the increasing exponents of x and not in the decreasing exponents of x. The Euclidean division that you used to know, you used to do it like this. You put like x2 plus x over x2 plus 1. So you used to put the polynomials in the decreasing exponents of x. You start by the largest degree, but in here we start by the lowest degree. In here it's x, and on this side it's 1, and then we start the division. We say x divided by 1, it's x, so x times 1 minus x2 over 2, it will give me this. I will do the calculation. I will end up with x3 over 3. I continue. x3 over 3 divided by 1, it's x3 over 3, and then I multiply. I have this, and then I obtain here x5. And when in here I have x5, so x5 divided by 1, it will give x5, a term that is not of third degree. Then I stop. my calculation. So I stop my calculation, and the quotient in here will be the finite expansion. So it's the same thing that I found when I did tangent x in here. Now, for the final paragraph of this chapter, I will talk about how to apply the finite expansions to find some interesting things. First, the first application is to calculate or to find the equation of a tangent. So if f is a function having a finite expansion to the order n in the neighborhood of a point x0, and if n is greater or equal to 2, so we have the expansion to an order greater or equal to 2, then the term of order 0, be careful, not the first term, the term of order 0, and the term of order 1 of the expansion, they will give me the equation of the tangent to the graph of f at the point x0. So if I take these two terms, then y equals to c0 plus c1x minus x0 is the equation of the tangent. Of course, you know why, because this is f of x0 and this is the derivative of f at the point x0. So it's the equation of the tangent. Moreover, if I take this term to the other side, so I put f of x minus this term equal all the other terms, then studying the sign of these other terms will allow me to know the position of the tangent with respect to the graph of f. And to study the sign of these terms, I will look to the first term, so the c2x minus x0 power 2. I will look to this term. In this case, it's power 2. It might be in other cases, it might be power 3, because if the term of power 2 have a coefficient c2 equals to 0, then the first term after the term of order 0 and term of order 1 will be x3. So again, I took the first and the first constant term and the term of order 1 to be the equation of the tangent, and then if I look to the first term, the first non-zero term after these two terms, and if I look to its sign around the point x0, it will give me an idea of the position of the tangent with respect to the graph of f. For example, if my expansion is like this, if it's f of x being equal to 1 plus 2x minus 3x3 plus whatever, then if this is an expansion around 0, then y equal to 1 plus 2x is the equation of the tangent, and f of x minus 1 plus 2x, which is the tangent, is equal to minus 3x3 plus x3 epsilon of x. So I look to the first non-zero term after these two terms, the equation of the tangent. And if I look at this term, when x tends to 0, if x tends to 0 minus, this term is positive, then before 0, the graph of f is above the tangent. And if x tends to 0 plus, this term is negative, then f of x, the graph of f of the function f, is below the tangent 1 plus 2x. So at the point 0, f of x, it goes through the tangent. If, for example, this term is 3x4, so that term x3 and x2 are not there, they vanish, they go to 0, then on both sides of 0, this term is negative. Then the graph of f on both sides of 0 is below the tangent, and this is how we do it. So we calculate the limit of f of x minus the tangent, which is the limit of the first term after the constant and the order 1 term, and this term, depending on its sign, it will give me an idea on the position of the tangent. Now for the second application is the calculation of the limits. In fact, to calculate the limit of a function f at a point x0, if we have the finite expansion of f, then all we need to do is to take the term of order 0, and it will be the limit of f at x0, the term of order 0 of the finite expansion of f. Now what's interesting is when we have a ratio. So when we have a ratio f of x over g of x, we need to check the expansion of f and the expansion of g. In fact, we don't need to calculate the expansion of the ratio to calculate the limit. We need to check the expansion of f and the expansion of g separately. So we have three cases. If the expansion of f starts with the order k, so this is the first order or the least order in the expansion of f, and if the expansion of g starts with the order L, so this is the least order in the expansion of g, then if k is less than L, it's like we are in this case. Let's suppose to simplify that x0 is equal to 0, for example. If x0 is equal to 0, so we are in a case like this one. If we have x2, for example, plus x3 plus whatever in the numerator over x3 plus x4 plus whatever in the denominator. So in this case, I'm taking, of course, the example of x0 equals to 0. If x0 is not equal to 0, then instead of x, you will have x minus x0. So in the case of x0 equals to 0, we are in this case. Then, of course, you can take x2 as a common factor in the numerator and x2 as a common factor in the denominator and simplify them, and it will lead you to something like 1 plus x plus etc. over x plus etc. Which means that the denominator will be going to 0 and the numerator will be going to 1, and the limit will be 1 over 0, it's infinity. But the sign of infinity, it will be plus or minus infinity. It depends on the 1 in here and the coefficient in here. So if, for example, here we have minus 1 and here we have 1, then minus 1 over 1 is negative, then the limit will be minus infinity. Now the second case is when k is equal to L. If k is equal to L, then you have something like this. So you have x3 in here, x4, etc., or x5, whatever. What I care about always is the first term, the first non-zero term. I didn't take x2 because it's not in there. The coefficient of x2 is 0. I take the first non-zero term in the expansion of f, and the first non-zero term is in the expansion of g. And then, of course, in this case, I can take x3 as a common factor in the numerator and the denominator and then simplify it. And then I will have something like x3 times 1 plus etc. x, of course, and then x3 in here, 1 plus x1 plus etc. And then everything in here will go to 0, everything in here will go to 0, x3 is simplified, and the limit will be 1 over 1, which is 1. Or, if the coefficient is not equal to 1, if it's, for example, 2x3 over 4x3 in here, it will be 2 over 4, and then the limit will be 2 over 4 or 1 over 2. And the third case, if k is greater than L, then we are in a case like if we have x4 over x3, then of course you can take x3 as a common factor and then simplify it, and then the numerator will be going to 0, the denominator will be going to 1 or whatever the coefficient of x3 in here, and then the limit will be, of course, 0 in this case. So again, when you have calculation of a limit, you don't need to calculate the finite expansion of the ratio. All you need to calculate the finite expansion of the numerator, and to find the first non-zero term, and also the first non-zero term in the finite expansion of the denominator, and then depending on the degree of these terms, you will be able to guess the limit of the ratio. So this is what we wrote in here for the case k equal R or k greater strictly than L. So we have three cases. It's whether infinity, 0, or the ratio. Let us take the example of ln 1 plus x over x. You know that ln 1 plus x, its expansion starts by x plus etc. It's minus x2 over 2 plus x3 over 3 plus etc. And then divide by x. So you see here you are starting by a degree 1, and here you are starting by a degree 1. So you are in this case. And in this case, the limit is the coefficient of the degree 1 in the numerator over the coefficient of the degree 1 in the denominator. So it's 1 over 1, so it's equal to 1. And this is a formula that you know from last year that says that the limit of ln of 1 plus x over x when x tends to 0 is equal to 1. So the limit when x tends to 0 is equal to 1. If I take another example, the limit, for example, of sine x over x when x tends to 0, also it's the same thing. It's, you have in the numerator, it's the limit when x tends to 0 of, in the numerator you have x minus x3 over factorial 3 plus whatever over x, so the coefficients are 1, so it's 1. And then in this, using this method, you can calculate all the formulas that you memorized last year about the limits. And the final application is to calculate the asymptotes. So to calculate the asymptotes, it means we are calculating something in the neighborhood of plus infinity. So a function f, we say that it has an expansion to the order n in the neighborhood of plus infinity if it can be written as follows. So instead of x, we have 1 over x, because if x goes to infinity, 1 over x goes to 0. So to find the equation of asymptotes of f, what we will do is that we take the function, we need to find its asymptotes, and then we do the change of variables t equal 1 over x. So because we need to find something around infinity, we transform it to 0 by this change of variables. And then we calculate the finite expansion around 0. And after we calculate the finite expansion, we replace again t by 1 over x. And what we will obtain something like this. We will do, of course, examples later, but we will obtain something like this. It's c0x plus c1 plus c2 over x plus 1 over x2 plus 1 over x3, etc. All the other terms will be like 1 over x. And this is logical, because if x tends to infinity, all these terms will go to 0, and you will be stuck with these terms, which is the asymptote, because when x tends to infinity, f of x will be very close to the asymptote. So you calculate again the finite expansion of f at t, which is equal to 1 over x. So you calculate this expansion until reaching a term of order t or greater, because if you reach an order t or greater, then you reach the term 1 over x or greater. So when you calculate the expansion to the order t, you will obtain something like, you will have something like c0 over t plus c1 plus t plus t squared plus etc. So when you replace by x, this will be c0 over x, c0x plus c1 plus 1 over x plus 1 over x2, etc. So when you have this, you will say that the term with c0x plus c1 is the asymptote, and the remaining terms will help me figure out the position of the asymptote with respect to the function. So again, as in for the tangent, I will look what is the sign of the first term, if it's 1 over x, or it might be 1 over x2 or 1 over x3. What is its sign when x goes to plus infinity if I'm studying the asymptote at plus infinity? If it's positive, then f of x minus the asymptote is positive, and then the graph of f is above the asymptote. And if it's negative, it's the other way around, it's below the asymptote. So this is how you calculate the asymptotes using the finite expansions.